Алло. Алло.
Прием, прием.
Здорово. Мы точно туда зашли.
Да, там даже вот запись идет.
Ну, это любой может начать же делать.
Ну, все это выглядит как какое-то аниме.
А мне вот интересно было, у нас будут какие-то квизы на алгебре?
Но она сейчас зайдет, спроси.
Никто не
Надеюсь,
знает.
что не
что.
сегодня.
Мне кажется, не будет.
Не, они точно должны быть. У нас
Да.
же...
Ну, в силабусе этого нету.
Разве?
Бля, буду.
Марк уже проверил.
Ну похоже, да, не будет никаких тестов. Будет только типа контрольной работы что-то. И все.
Hello, everyone. Let's get started. First of all, I ask you to turn on your cameras and microphones if you can. I will be very pleased to see you. So, thank you, Artyom. And Ale. Nice. Hello, Tamara Vasilyevna. So, what's where is my window? Do you now see and hear me? No?
Yeah, we
Yeah.
do.
Okay.
We do hear you, yes.
Nice, okay. Right, okay. Let's start. I hope you've already done your homework, and if you have some questions, you may ask them. Questions about homework.
I actually do have a question about homework.
Okay, let's discuss.
Yeah, so one of the axioms for subgroups is that if, from what I understand, so what is stated is that whenever there exists an inverse, there exists an element. It was something like that. And for the second number, we have a set from 0 to 5. And for instance, the inverse of 5 is 1/5, but it's not a whole number, thus it does not belong to this set.
Mhm.
So would this imply that the set in the second task is not a subgroup, or am I getting something wrong?
Okay,
Inverse
let me have a look. What number? Second problem.
Yeah.
So
there-
what's the operation here in our group? You have
Addition.
addition, and the inverse number according to addition is such a number that our number plus this number equals a neutral element, which is 0 in our particular case, right?
Yeah, so we would need
the
negative
inverse,
5. Okay.
yeah.
No, it would be
5, for example, plus 5 plus 1 equals to 0 modulo 6, right?
Mhm.
So the inverse element depends on the operation here. And if you have a multiplicative group, you have to find some element that 5 multiplied by this x equals 1, which is a neutral element in case of multiplication, modulo, for example, 6, if you wish. Okay? Okay, next question.
Is it questions about homework?
Yes, this is a questions about your home task. We discuss not particular problems because you have to solve them on your own, and you have to tell your solutions to your teaching assistant and so on. But we discuss some definitions, some things that are not as clear as we want. Okay, let's start with our problems for our today's practice.
are they already given on the site? I mean, the set of problems on Wiki. On Wiki. Is it there or?
The set of problems for today, it's on Wiki.
Okay.
I can show you. But I prefer to share my paper with you. So for the first problem, let's have a look. Here, you see now our first problem is to find cosets of some subgroups in our symmetrical group of order 3, where sigma equals 1, 2, or 1 to 3. So this is our problem, and I'm going to tell you how to solve this problem, and I hope you'll ask me questions if something is unclear. So let's start with this problem. So I hope everyone sees my papers. My notes. Yeah, right. Okay. First of all, we need to define which is our group generated by sigma. So this group. As you know, this is a cyclic group, and every element of this group has the same the following form. This is sigma to the kth power, where k is a natural number of 0, right? So these are the powers of this particular element. In S3, what do we gain if we take this permutation and the permutation to the 0 power equals the neutral element of this group to the first power. This is this particular permutation, and when we multiply this permutation by itself, we obtain neutral element, right? So this group generated by sigma consists of 2 elements, neutral element and sigma. And let's define, so let's solve our problem for this group. We need to find cosets. Which is a coset? We have to take some tau from our symmetric group, and tau multiplied by our subgroup is a left coset of tau. Right? And this one is a right coset. Sometimes it turns up that we may take something else. Het tau, for example, and our left coset will be the same as with tau. That's not a problem. Sometimes it occurs. So in our groups.
Wait, excuse me, is this tau where the subscript a different tau from ours, or like why do we have to consider it?
This is a different tau. Sometimes it takes place that we take another tau and the cosets are the same. For example, the example is very simple. Take this subgroup consisting of the neutral element and our permutation, and let's consider the coset of neutral element, which is equal to our subgroup, right?
Mm-hmm.
And the coset of our permutation, which is also equal to our subgroup, because this permutation multiplied by this one is our permutation, and multiplied by this one is neutral element, right? So the left cosets of different elements, neutral and our permutation, are the same.
Mhm.
So it's a natural example if we consider groups. So
In these cases, even the left coset is equal to the right for both ones. Yes.
sometimes not.
I mean, in this case, when we have to take the left coset of the identity element and of our like sigma multiplied by
You're
No.
right. If we take every element which is in our subgroup and find left and right cosets of the elements which are in our subgroup, the left and right cosets will be the same.
Mhm.
Because the left and right cosets will be the same as our subgroup.
Excuse me. What does mean the height of the tau means?
This means that I took some other tau, some other element. I don't know for sure what the element is. Okay?
Okay, got it. Yeah.
Sometimes it takes place, sometimes not. So never mind now. Okay, then let's find cosets. We have to multiply our elements from our subgroup by different elements of our symmetric group, right? So the first coset is the coset of the neutral element. We've seen it already, yeah? The second one, let's multiply our permutation by some other transposition. For example, this one. What do we have? 1 goes to 3, and 3 goes to 2, and 2 goes to 1. Yeah?
Mhm.
This is a 3 cycle. That means that the right cosets. This is our sigma and our transposition. The right coset is the following. E multiplied by 1, 3 equals to the neutral element. It's equals to our transposition. It's clear. Yeah? And the product of our non-trivial element and our transposition equals to 3 cycle. Okay?
Mhm.
So this is the second right coset. The next one.
But, excuse me. Okay, we're considering it in S3. Yeah. So
Yeah, S3.
okay.
Symmetric group of order 3. The next one, let me take some other transposition, and we ran out of transpositions now. We considered all of them. Here we have 1 goes to 1, 1 goes to 2, 2 goes to 3, 3 goes to 3, and 3 goes to 1. This is also a 3 cycle, right? Okay, then the third coset is the following. Sigma multiplied by transposition to 3 equals to the set of transposition to 3 and 3 cycle, 1, 2, 3. Do I have to find some other cosets?
Didn't we just consider right cosets?
Yeah.
Yes, we only considered right cosets.
We only considered right cosets in this case. Left
So-
cosets is a exercise for you for your own work. So my question was, did we find all cosets, or we need some else?
Don't we have to also find the coset of sigma? I mean sigma generator multiplied by sigma as we did it before.
Yes, but I know that I multiplied the subgroup by sigma. I'll have this particular subgroup. Yeah. So this is the same coset as the coset of the neutral element. Look, how many elements do we have in a symmetric group of order 3? There are 6 elements in S sub 3. Yeah. And how many elements do we have here? 2 elements here, 2 other elements here, and 2 last elements here. So all the elements of our group are in these cosets. This is the coset of neutral element of a transposition 1, 2. This is the second one. And the third one is here. Do you remember the Lagrange theorem from your lecture? So, how can we apply this theorem in this case? We have a subgroup consisting of 2 elements, subgroup generated by sigma. And we have a group which consists of 6 elements. And the number of right cosets, denoted by S3 colon sigma generated, equals to the number of elements in our group divided by the number of elements in our subgroup. This is the Lagrange theorem, right? So it works successfully here. The next one, we have to find cosets of a subgroup generated by a 3 cycle. Let's find them. But previously, let's apply the Lagrange theorem to our case. How many elements are there in this subgroup? The elements are the neutral element, the transposition, and the square of this transposition, which is, not the transposition, excuse me, the square of this 3 cycle is another 3 cycle, right? How many cosets do we have in this case? According to the Lagrange theorem, they are, how many of them? How many of them?
1. Oh, wait.
Not 1. We have a 3-element subgroup in 6-element group. Here is a 6-element group, and here is 3-element subgroup. So the number of cosets is 2. What is the first coset? Let's find left cosets in this case. E multiplied by our subgroup, which is our subgroup. What do we know about the next coset? How many elements are there in each coset?
1.
Why?
Because there are already 3 elements in our cyclic group.
So
In every element could be only one. In every right and left coset can be only 1 element, because then we have total 6 of them.
We have 6 elements, but we have 2 cosets, so we already have 3 elements in the first coset. So in second, we also have to have 3.
agree. agree. This explanation is clear to me.
I-
Do you have
Can
any
you
questions concerning the second explanation?
Excuse me?
can you please scroll your paper up because it's impossible to see what's okay.
Yeah. Mhm.
Like,
So, according to the Lagrange's theorem, we have two cosets. Yeah, the first coset consists of three elements here. Yeah, and we have the second coset, right? How many elements are there in the second coset? The same number of elements which is in our subgroup, because for every element of our symmetric group, what is a coset? It's the set of elements of the form tau sigma, where sigma not tau, for example, delta, where delta in our subgroup generated by sigma. So there are the following elements: tau sigma squared, and tau sigma cubed, which equals to tau, because sigma cubed equals the neutral element. Yeah? So every coset consists of the same number of elements as our subgroup, because we can find this number of elements multiplying our particular tau to the elements of our subgroup. And every two elements of this sequence are different, because, for example, let's tau sigma be tau sigma squared. Multiply this equality by tau to the minus first power, and we gain that sigma equals sigma squared. But it's contradiction. It's not true in our group. Sigma doesn't equal to sigma squared. These are two different elements. So all of these products, tau by some elements of our subgroup, are the different elements. So in our case, the left coset of some other element, let's take the transposition 1, 2. It is a set of the rest elements, our symmetric group minus our subgroup. Because we have two cosets according to the Lagrange's theorem, right? And every coset consists of three different elements. And moreover, all of our cosets don't have common elements, right? From the lecture, you know that if we take two cosets, then they are either the same cosets or they don't have common elements, right?
Mhm.
but why do we take this permutation 1, 2? Like, why not 1, 3, for example?
You
not?
can take 1, 3, for example.
Do we
I took some permutation which is not in my subgroup, because if I take the permutation from my subgroup, I gain itself, right?
So, like in this case,
And I need another cassette, so I take some other element. But in this case, it turns out that it doesn't matter what other element do I take. The second coset is the same for every element which is not in our subgroup. But only in our example, because
Excuse
the
me.
second. Mhm.
Is it true that S3 exclude all this permutation which is generated by E times 1, 2, 3?
Yeah,
So
you're right.
If we take any other permutation then this E, then we get the rest of the element in the whole group.
Yeah. You may check it by direct computation, but using the Lagrange's theorem and using our knowledge about subgroup and cosets, we can gain it without any computation. And that's true.
Okay.
What you've written in the chat. Yeah, it's true. It's absolutely true. Moreover, let's consider right cosets. What if the right coset of the neutral element is our subgroup? Yeah? And what if the right coset of some other element? This is our group minus our subgroup, right? So this is the left coset of element 1, 2. But only in this particular case. You may compute the left cosets in the previous case, and you'll see that right cosets and left cosets are not the same in the first case, where we've considered a subgroup generated by transposition.
Okay.
Okay. So do you have any questions? No questions. Let's go on and solve the second problem. The second problem is the following. We have a group which is a symmetric group of order 4, and H is a subgroup in our group. Which subgroup? It consists of all permutations sigma such that sigma of 4 equals 4. So all these permutations don't move 4. Yeah.
So
We
like
have-
it's excuse me. So like it's a cycle of length 3 and cycle of length 1, like singleton.
For example, this one, yeah, and this cycle, for example, yeah, they are in our subgroup. You're right. Then, what shall we do? We have to show that H is not a subgroup, strictly speaking. It's a subset now, but we have to prove that H is a subgroup. And we have to find it left and right cosets. Okay. Let me have a look. First of all, we prove that H is a subgroup. What shall we do? This subset H is associative. The neutral element belongs to H because the neutral element does not move any element of our set, not only 4. And if I have an element and it doesn't move 4, so sigma of 4 equals 4, and I have the inverse element, which is in S4, sigma to the minus first power of 4 equals 4, right? Do you agree?
Mm-hmm.
Yes.
Okay, so the problem is the following. We have to take sigma from H, tau from H, and show that the composition of these two elements is also in H.
It's very easy, in fact.
It's very easy because we have to apply the composition to our element, which is, firstly, we should apply tau and then sigma, and this is sigma of 4, which is also 4. It's simple. So we obtain that H is a subgroup. the next point, we have to find left and right cosets of H. Let's find them. First of all, let's find the number of cosets. How many elements are there in H? The number of elements is the same as in S3. Do you agree? Because the elements of H acts on our set 1, 2, 3, 4 as elements of symmetric group of order 3. They move these 3 elements and they don't touch 4. So
sorry for interrupting, but in proving that H is a subgroup, haven't we checked associativity?
I said that associativity is not a problem because the elements of S4 are associative. The multiplication is in S4 is associative. It means that if we take some elements of S4, not all elements, but some of them, the multiplication on these elements will be associative.
Mm-hmm.
Okay?
Yes.
Right. So let me write down for all. We know that for all A, B, C belonging to S4, A, B, C equals A multiplied by BC, right? We know it from S4. And for every element A hat, B hat, C hat in H, which is in S4, we can write down the same.
I think I got it because our subset H will be equivalent to S3, and which is a group and which has associativity.
You're absolutely right. You're absolutely right. This is the second point I'd like to discuss with you. It is very helpful for us because using this point, we know that the number of elements in H is the same that in S3, right? These groups act in the similar kind. So the number of elements in H equals 6, and the number of elements in S4 equals 24. Do you understand why?
Yes.
Because here equals 2 by 3 by 4, yeah? So we have 24 elements in our group and 6 elements in a subgroup. So the number of cosets, according to the Lagrange's theorem, equals to 24 over 6, 4. And let me guess, what are these cosets? I guess that the difference between these cosets is the image of the element 4. Let's see. So I claim the following thing. The set of these cosets is the following. Sigma I takes 4 and move it to I. So and it doesn't matter what sigma 4 do with other elements. So this is my claim. Let's check. Let's see. First of all, so we have to show that if 2 elements acts equally on the element 4 of our set, 1, 2, 3, 4. They are in the same left core set. And if they act differently, they are in different core sets, right? Are you still with me, guys?
Yes.
Can,
Yes.
can
Okay.
you repeat this point? I didn't hear.
So I'm trying to guess what are these core sets. I take H and multiply it by different elements of our group S4, and one of these core sets is of have one of these core sets has this type. So let's take the neutral element and multiply it by H. What do we have? We gain a set of elements which are the following type. They act on 4 equally. They don't move 4. Yeah? It's isomorphic to our S3 group. It's H, okay? We take
Yes.
H multiplied by the neutral element and we still have H. Or we can multiply it by any other element which is in H. So our sigma sub 4 is an H. It does not move 4. So it's an H. And we'll see that we can take any other element which moves 4 to 3. For example, sigma 3, some element. It doesn't matter how it acts on 1, 2, and 3, but it moves 4 to 3. And the full core set consists of all the elements which move 4 to 3. Okay? So how we can check it? For example, I have some element tau, and I know that tau of 4 equals 3. I have to show that tau belongs to sigma 3 multiplied by H. Which is tau? Tau equals to sigma 3 tau sigma 3 to the minus first power, and that's all. Yeah. So I have to show that this element belongs to H, right? So sigma 3 to the minus first power of 4, which is that? I don't know the image. I know that sigma 3 takes 4 and moves it to 3, right? But I don't know what it makes with 4. Let me have these elements in some other order. Sigma 3 minus first power, sigma 3 of 4. Sigma 3 moves 4 to 3, so it's equal to sigma 3 to the minus first power of 3, right? And then sigma 3 to the minus first power of 3 equals 4. Okay? Is it clear, guys?
It's not.
Yes.
It's clear, yeah? So I took some element which acts on 4s sigma 3 and showed that these elements belongs to this coset of the element sigma 3.
Sorry, for me it is not clear.
Why?
Because here we, like in the bottom right corner, we like just erased sigma 3, and I don't get why.
We know that sigma 3 of 4 equals...
Oh, wait, sorry, I think I got it.
Right, yeah, okay. Okay, some other questions? No questions? Okay, so what did we show? We show that every element which acts in the same type on 4 belongs to this particular coset. It doesn't matter that we've shown it for 3, we can do the same thing for 2 and for 1, right? So, but we have to prove that these different kinds of elements cannot belong to the same coset. Let's imagine that we have tau and sigma. Tau of 4 equals I, and tau of 4 equals j, and I doesn't equal to j. Yeah, and suppose that tau and sigma belongs to the same sigma k h, to the same coset. Yeah. When tau belongs to sigma k h, if tau equals to sigma k h for some h from h, yeah? What does this element do with 4? Moves it to k, right? So tau moves 4 to k. What does this one do with 4? Sigma, which equals to sigma k h hat, where h hat from h. It moves it to k, right? So these two elements, tau and sigma, have to move 4 to the same element of our 4-element set. And they belong to the same coset if and only if they act on 4 in the same way, right? So we've solved this problem for left cosets. Do you have any questions?
Can you please move the paper in the middle of the screen?
Okay.
Thank you.
Where else? So I have a question. I have a question concerning the right cosets. Could you guess what are the right cosets in this case? Okay, let's have a look. Let's have a look on...
Wait, about previous explanation, I didn't get why both of them equal k.
Why both of them equal to k? Because if tau belongs to this coset and sigma belongs to this coset, implies that tau is a product of some element of this particular element, sigma k, and some elements from h. And tau is a product of this element, the same element sigma k, and some maybe other element from H. And we considered the image of 4. The image of 4 here is the image of H4, and H4 equals 4 because H acts on 4 equally. Yeah? And sigma k of 4 equals k. We know it. We defined these cosets in the following way. And here we see that H hat of 4 is 4, and sigma k of 4 is also k. So sigma and tau should act equally.
Okay, think got it. Think that I got it.
Okay. So about the right cosets, let's consider some right coset H sigma. Sigma acts on 4 equally, yeah? Not sigma, H. And here, sigma, what should sigma do? Sigma should take some element, I, and move it to 4, yeah? And then H acts on this 4, okay? So the difference between different cosets is the element which goes to 4 by the act of sigma. Did you get it? Who can name all the cosets? My claim is the following. The right cosets are the following cosets: sigma, say delta 1, H delta 1, H delta 2, H delta 3, H delta 4, where delta I of I equals 4. So the difference in between the cosets in this case is the element which goes to 4. So, like in the previous case, we have to show that if two elements act on some I, such that I goes to 4, they are in the same coset, and if they are not in the same cosets, they act differently. So let's check it. So I have some element, say sigma of I equals 4, and sigma equals something here, and for example, sigma of 1 equals 4. Delta 1, and something here. What I know that delta of 1 equals 4, and I have put there delta 1 to the minus first power, and here delta 1, yeah? So delta sigma, here is sigma, yeah. Sigma of 1 equals 4, delta to the minus first power of 4 equals 1, because delta 1 of 1 is 4, delta 1 to the minus first power of 4 is 1, yeah? Here 4, here 1, and delta 1 of 1 equals 4. And this element belongs to H, because it acts equally on 4, right? So here we have that sigma equals some element h of h sigma. But strictly speaking, I have to show not this one, but I have to put sigma equals something of h delta 1. Yeah, I have to put delta 1 here, and I have to put delta 1 to the minus first power sigma here. That will be correct. That will be correct. So here it's not, it's correct. The equality is correct here, but it doesn't prove our effect. Do you understand why? I need to show that my element sigma equals to h from h capital multiplied by some delta. For example, delta 1 in our case. Yeah? So I have to write down sigma delta 1 to the minus first power delta 1 here in this case. And of 4 it equal to sigma 1 of delta 1 of 4, delta 1 of 4, no, delta 1 to the minus first power of 4, it's 1. Delta 1 of 1 is 4. And sigma, what? Do you see some problem here? Guys, are you here? Are you still with me? Are you solving this problem?
Yes.
The problem.
But can we consider some problem which is based not on, like, the group which is based not on permutations, because permutations like makes it too complicated.
I agree.
So we'll have to solve this particular problem concerning permutations, because the definition of our subgroups and all the things, all the stuff in our problem, it's about permutations. So let me explain. The problem is the following. I fixed some particular permutations, delta 1, delta 2, delta 3, delta 4, which act in the following type. Yeah? And I have to represent our permutation, which puts I2, 4 as some permutation from our subgroup multiplied by this particular delta. Yeah?
Mm-hmm.
If I write down something like that, sigma multiplied by delta.
But I have a question.
Yeah.
And this sigma does not belong to our subgroup.
This sigma doesn't belong to our subgroup. This sigma is some element of S4.
Mm-hmm.
Okay. So, what what do we have? Sigma can be represented in the following way, because it's an identity, yeah? But we have to represent it in the way where here is some element of H, and here is our particular delta, yeah? And the problem is to prove that
I have one more question. And
Yeah.
what's the difference between sigma with with index and sigma without index?
Sigma without index is our sigma, some element from the group, which acts as delta.
Mhm.
And delta is a particular element, and we know that this particular element acts in the following way.
Okay.
So this is
Okay.
an arbitrary element, and this is a fixed element. Yeah.
Mhm.
So this is the difference. And why this one belongs to H? Why? Because let's take this one and apply it to 4, because H of 4 equals 4. We have to prove this. Apply delta to the minus first power to 4. What do we have? Delta 1 of 1 equals 4. Delta 1 to the minus first power of 4 equals 1. So this is 1. And sigma of 1 is 4. So this element acts equally on 4. So sigma delta 1 to the minus first power belongs to H. This solves our problem. So the question for you is to find...
No, sorry for interrupting. Now I don't get why our sigma of 1 equals to 4.
Sigma y delta 1.
No, in the
Delta
last
1
row.
equals to 4 because we denoted this element in this way.
But it was about the fixed ones with index.
Yes, this delta 1 of 1 equals to 4.
Okay.
Yeah, and delta 1 to the minus first power of 4 equals to 1.
Yeah. It like in back in opposite direction.
Yeah.
But I mean last row when we когда мы избавились от дельта в последней строке, мы пришли к тому, что у нас есть сигма от 1. Вот, да, именно это место. Почему это равно 4? Мне это вообще не очевидно.
Okay, we took sigma, and our intention is to show that if we take some arbitrary sigma which acts as delta I here, sigma of 1, I should write down sigma of 1 equals 4. We take this sigma which acts on 1 in the following way, and we show that it can be represented as the product of some element of H and this particular delta 1. Every element which acts on 1 in this following way can be represented in this way, using the fixed delta 1, which is the common for all the sigmas which acts in this way. So this is the explanation. Is it more clear or not than previous one?
And now I don't...
Минутка объяснения на русском. Наша идея в том, что мы хотим показать, что любой элемент, который единичку переводит в четверку, можно представить в виде что-нибудь из h умножить на вот этот конкретный дельта 1. Всякий элемент, который единичку переводит в четверку, можно представить как элемент из h умножить на дельта 1. Понятно?
Да.
Мы это и показываем. Вот.
Все, кажется, я понял.
Okay, then, so here, in the previous part of the explanation concerning the left cosets, we had to show that this tau doesn't equal to this thing. This tau equals to sigma 3 sigma sigma 3 to the minus first power tau, and this element is belongs to H. So the proof is the same, like in this case. You see? So let it be an exercise for your work. Okay? If you have any questions, please ask them, and we'll move to the next problem. Okay. Okay, let's prove the third problem. The third problem is the following. We have complex numbers, and the operation is multiplication. Complex numbers without zero form a group according to multiplication, and H is a subgroup which consists of all elements on the identity circle here. You see, this is a complex plane, and here we have this set H. We have to show that H is a normal subgroup of G, and we have to find its left and right cosets. So why H is a subgroup? Let's take Z1 and Z2 of H and their product. What do you know about the length of the product? We can write down the following thing. So it equals to 1. So H is a subgroup. Am I right? Am I right here?
Yes.
Yes. Should we check something else to prove that H is a subgroup?
That identity element is also there. Like
Identity element is also there. Associativity is here, and the inverse element. The length of the inverse elements is the same. Yeah.
Mhm.
For our elements, the inverse elements are also on this circle, right? So let's take this one. This element rotate our plane by phi, and the inverse element by phi clockwise. This one counterclockwise, this one clockwise. So this is a subgroup. Let's check that this subgroup is a normal subgroup. How do we check this? We have to take some alpha from our group and multiply some z from our subgroup by alpha and alpha to the minus first power, left hand and right hand, right? So here equals to alpha to the minus first power z. It equals to that because complex numbers are commutative. Agree?
Yes.
Okay, complex numbers are commutative, so it implies that for every alpha, alpha
But
to the minus first power belongs to H. Yeah.
But we didn't prove that they're commutative, actually.
Now we did not prove it, but I suppose you already know it from, for example, calculus. Am I right? No?
We briefly
About the
considered
complex numbers.
them
The linear algebra.
Yeah.
You used them in linear algebra, yeah? And you proved the properties of complex numbers there, right? No?
We might have done this, but it was quite long ago.
Okay, let it be a simple exercise for you. You have to prove that these two numbers commute. Okay? Could you kindly
Okay.
do it on your own, please? Okay, nice. So this shows up us that H is a normal subgroup. Every subgroup in a commutative group is normal. You see here. So we showed that H is a normal subgroup, and we have to find the left and right cosets. So I claim that left and right cosets, which are the same sets, because this subgroup is normal subgroup and all these numbers are commutative. The cosets are the sets of elements of the same length. Let R be a real number, non-zero real number. So this is a left coset, one of the left cosets, and all the left cosets are the numbers of the same length. Yeah. Okay. Why? Let's check it. We can show for every number, say z, it equals to z multiplied by z over its length, right? Because z is a non-zero complex number, right? So this one is equals to some r, which is real, and this belongs to H, right? Because we took some complex number and divided by its length. Yeah. So this guy belongs to RH, right? It looks like the left coset. And if we take two numbers, Z1 and Z2, such that they are not of the same length, and try to represent them as RH or RH1, where H is H and H1 are the elements of our subgroup, and R represents the coset. It shows us which particular coset we take here. And this equals to Z2. So we have to, they're not equal. I'm sorry. The lengths of these numbers are not equal, but the cosets are the same. So what do we have here? let's find the length of Z1. It is the length of R by the length of H, which is R because R is a real number, and moreover, the number is being the modulo of Z is it's not negative, it's positive. It's positive, it's not zero, it's not negative. So it's R multiplied by the length of H, which is also which is 1 because H belongs to the set of these kind of numbers. Yeah. And here, what do we have here? Here we have R by 1. Also, R by 1, right? Guys, some questions?
No, till now everything is pretty okay.
Everything is pretty okay. So the cosets, how can we show them on our plane?
Maybe to to throw whether they satisfy the properties. I mean, we may just multiply this left side to our set.
So we take our set H and multiply every number by, for example, 2, representing the length. And so we obtain another circle, yeah? And all the cosets are the circles, and the radius of this circle is the length of these particular complex numbers, right? So these circles are the cosets.
Mm-hmm.
Okay?
So only the radius changes, but not the operations.
Yeah. Okay. Then what's next? The next one is the problem number.
Sorry for interrupting. And we do not need to find left cosets and right cosets because the operation is commutative.
You're absolutely right.
Okay.
The reason,
they're both left and right cosets to itself.
they are left and right cosets of this subgroup.
Okay.
Every left and right cosets are equal. Here we go.
Thank you.
And we've described them as cosets using only real numbers here, only positive real numbers, but you understand that if we take all the non-zero complex numbers and take all their cosets, the set of cosets will be the same as for only positive real numbers, right? Because only the length is important in this case. Okay, then number 4. We have to describe all the subgroups of such kind of a group. Do you remember what is this group? What does it look like?
Like numbers from 0 to n.
n-1.
You're right, to n-1.
And the operation is
Or from 1
plus
to n,
with
what is the operation?
is addition with modulo n.
Right. Right, you are. And this is a group. You know that this is a group, I suppose. Let's describe their subgroups. Let's remember the theorem, very useful theorem from the lecture. I mean Lagrange's theorem. What is it? What does it give us in this particular case when we speak about the subgroups? What do we know about subgroups according to this theorem? Maybe we know the number of elements in subgroups.
Like the number of elements in subgroups is just like the order of every element.
The number of elements in each subgroups is?
I mean the order of each element of this set. Or each
It's not true because there are, for example, elements of order 1 in every group. Yeah, the neutral element. Its order is 1. And I mean this one. Suppose G is a subgroup. Then the number of elements is a divisor of the number of elements in our group, which equals to n. So the number of elements in a group is divisible by the number of elements in a subgroup. Okay? So
wait,
yeah.
be different. Okay, it's divisible. Okay, I got it.
Yeah. Okay, then how can we describe the subgroups? If we take some element, say A, from our group and take a subgroup generated by A, which consists of 0A, 2A, 3A, etc. The number is finite. Yeah, this is a subgroup. Okay. And my claim is, for every G, which is a subgroup of our cyclic group of order n, exists such element G that this element generates our group. So having one element, we can generate a subgroup, but my claim is that if I have a subgroup, I can generate it by only one element of this subgroup.
Well,
Why?
isn't it obvious? I mean, just by definition of a generator, generator generates a
it's not such obvious because now I take some arbitrary subgroup of our cyclic group.
Okay.
You know that every subgroup of a cyclic group is cyclic. If you know this, it's obvious. Yeah?
Yeah.
Okay, so it's obvious.
Wait. I have a question. And why we cannot consider a group which consists only neutral element, subgroup which consists only neutral element?
We can consider this group and it
no, not group, subgroup.
Subgroup and
can we consider
what's the problem?
Can we consider a group which consists only neutral element?
Surely.
Okay.
And this group can be generated by this particular neutral element because all the powers of this element are the same. Okay. They are all this neutral element because we consider trivial groups. So we know that, we already know that, that's nice. For every subgroup of cyclic group, G is a cyclic group. It's very nice of you to know this. So we have to describe all subgroups of our cyclic group. So all the subgroups will be cyclic. And they are generated by some elements of our cyclic group of order n. Let's take every element of our group, of our cyclic group of order n, and generate a subgroup. But sometimes we'll have the same subgroups. For example, let's take a cyclic group of order 3 and generate a subgroup by this one and this one. Yeah, they're the same subgroups.
Excuse me.
So yeah.
We had the same issue in our homework, for example. I just wanted to wonder, I didn't like consider this in a separate case in our homework, but for example, if we have two generators which generate the same sets, but these sets are differently ordered, they are still the same, yes?
If we have, I didn't get it.
Like, for example, in our homework, we had two...
In your homework, in your second or first one?
First, but like we had something like, for example, the group, the subgroup generated by 2, it was 0, 2, 4, and the subgroup generated by 4, it was also something like 4, no wait, 0, 4, 2. Like they have different order of elements, so they are still equal, yes? I mean, this with no regards to the order of elements.
First of all, the order of 2 and 4 in cyclic group of order 6 are the order is the same. It's 3. Yeah.
No, I just mean the different order. I mean whether the group is ordered. I will provide this in our.
The group is not ordered because we don't discuss order concerning order and its connection with the operations. Yeah.
So like for example, the group 0, 2, 4 is equal to the group 0, 4, 2.
Yeah,
okay?
Because what's the group? What's a group? The group is a set and an operation. What are sets? Sets are the same. Sets are unordered. Sets are the same. What is the operation? The operation is the same as in our whole group. Yeah. So the operation is the same. Addition modulo 6, as I understood. Yeah. So the groups are the same. Yeah. Right.
Okay.
Absolutely right. So okay, we ran out of time, but I propose you to solve this problem and then end our class. Yeah. Do you have any other classes after our class? No. Okay. Let's solve this problem and that will be all. So. All of our subgroups. What do we know about our subgroups? Our subgroups have some orders, which are divisors of n. Yeah, and are generated by one element of our group because all the subgroups are cyclic. So you have to take different elements and generate subgroups by these elements. And for every m, which is a divisor of n, we can find a subgroup. Yeah, because let's say that our group generates by a. Okay, our group can be generated by 1. And let's take n over m. This is a whole number because m is a divisor. And let's generate an additive group using this guy. Yeah. What's the order of this element? We know it's m. Yeah. Because we add it m times by itself, and then we take n, which is 0 modulo n. So let's take all these elements for all the devices, yeah, and we'll have some subgroups. Why there are no other subgroups? Why? Because every subgroup can be generated by one element. The number of elements, we know the number of elements, and how can we find some particular kind of generator? We may consider G such that it's the least positive number in G, the least positive remainder, modulo M. And this remainder have this particular form, you see? And it generates a group. Because if we take G, which is least positive in G, and consider 0G, 2G, 3G, they are all in the group, yeah? And all the other elements are some K multiplied by G. You used this when you proved that every subgroup of a cyclic group is cyclic. Because if we take some M and say that this is QG plus some remainder, this remainder is also in the group, and this takes us to contradiction. Okay, so this shows us that we described some cyclic subgroups, and these cyclic subgroups are all the subgroups of our group. Okay, unfortunately.
Wait,
yeah.
I have a question.
Okay.
For example, we have like we can have not only one, but infinitely many, not infinitely many, but some of these subgroups here, cyclic subgroups.
Mm-hmm.
For example, one is based on one element, and other like one based on one, and another based on two,
Mm-hmm.
and etc.
Mm-hmm.
But at some moment we can, it is not infinitely large group. Okay, I got it.
Yeah, okay. Mm-hmm.
It is limited by n, and therefore like I think I got it.
Okay, yeah, it's limited by n, and it's limited by the property that they are devices. Mm-hmm. Okay, so guys, today we don't have a QA session about after our class. Let's have this one on Monday, because today I cannot hold Q&A after our class, but on Monday, but please check the time on Wiki on Monday morning, because it can be changed. So something about 4:30 p.m. or even 6 p.m. What do you think about this time? Is it appropriate for you?
Yes.
Okay, so let us meet the next week on Thursday as usual. And if you want to visit Q&A, join us on Monday evening, but I'm not sure what's the time. Please check it on Wiki on Monday morning. Okay, so that's all. If you have questions, please ask them now or on the Q&A. I suppose no questions. Okay, thank you for our class. Good luck and goodbye. See you.
Thank you for the seminar. Goodbye.